And thank you for showing up, right after lunch. It's always a difficult time slot. Okay, so let's begin with a quick recap of, my last year and to please the marketing team. So I've been focusing on two things. One was shipping Hitman, which is going to be in store pretty soon. And the other half of my time was trying to lay down groundwork for technology for the future titles. And of course, the bulk of our focus for that tech was really on animation, which is what I'm going to be talking about today. So let's begin with a little bit of a history of the animation technology at I/O. Historically, we've been running on our own tech, which we call the Glacier 2 engine. And when it comes to animation, since the days of Hitman Absolution, we've been relying on the Morpheme middleware. Okay, so we were kind of early adopters for this, and it also meant that we started forking and optimizing it kind of very early on, which basically meant we found ourselves a little bit on a dead-end route, where basically it was very hard for us to keep moving to a newer version of Morpheme. We use this for our hero and for our NPCs, and then we have a separate tech stack pretty much for our crowd. You can find the details about the crowd animation in this talk from Michael Butner from GDC. So this is pretty much the tech that we used up to this point, and even on Hitman 2. It's okay, but it's showing its age. It's really starting to feel like a constraint, pretty much. So we really wanted to, prepare for future titles to do something new. So some time ago, around 2007, we started looking at, okay, how can we upgrade at least to the latest version of Morpheme? We started doing that work, put engineering hours into, getting on the latest version, but timing was kind of bad. Basically, NaturalMotion and its parent company, Zynga, they decided to cancel Morpheme. So after many months of engineering, we find ourselves having to throw all of that basically out of the window and just shelve those animation updates and refocus on shipping Hitman 2 basically with what we had. Some time passed by, we got a chance to, the game was full in production, and we got some time to go back and reevaluate basically what were our options for animation. And this time we actually decided to start developing something new internally. So question is, okay, year before you were basically going for a middleware solution, and only a few months later you're now planning to do in-house technology. There are, of course, multiple reasons for that. I mean, one is that our middleware of choice, previous choice, basically was not available anymore. When we looked at the animation middleware market, also, it feels like it has been shrinking recently, and many of the previous players have kind of disappeared or acquired by larger companies, pretty much. Also, selecting something and then seeing it disappear only a few months later, but still having put engineering effort into it, something that can really, leave a scar. So we really didn't want to have that again. But all in all, the real reason was that we believed that during that time frame, motion matching and similar technologies were kind of proven as a viable option for AAA titles. So it really, AAA games using that tech started showing up on the market in that time frame. If you're not familiar with motion matching, it's a relatively recent animation technology that kind of flips the way you do animation in games. Upside down. Generally, or let's say more conventionally, your gameplay code will ask your animation systems, things to combine, stuff like, hey, I want to have 50% running, 50% walking. Please compute, some middle ground. Motion matching works the other way around. So your gameplay code is meant to really provide a goal that it wants to achieve. I want to move along this trajectory with this speed and this style, and then it will look at the data set and will try to pick something that fits your goal, that basically matches your motion. It's very similar conceptually to parametric blending, which is also something that, as an industry, we've been doing for the last few years. But this one really embraces, a data-driven approach, where you literally throw tons of animation data into the system and let it really figure it out how to do it by itself, pretty much. And as I was saying, AAA titles have been shipping in that period using that tech. For Honor, it's probably the main mention, but FIFA 18, FIFA 19, UFC, and other titles from Electronic Arts are also powered by similar approaches. There are GDC talks documenting this and what are the differences between the various systems. But the key idea is pretty similar. And there are many more games in development as of today that have fully embraced this technology for their animation technology moving forward. So we looked into motion matching. We did a tech assessment, and basically our conclusion was that it can be used to replace or simplify large sections of what we're currently doing in our animation graphs in our Hitman games, pretty much. It's very well suited for everything that is related to locomotion, for instance. At the same time, we also don't believe that it can replace it all, or that maybe even if it can, it might just not be worth it. And I'm thinking about stuff like in-game cutscenes, parametric aiming spaces, head look at, just more general upper body layering, and those kind of things. Things that are basically simple enough to be solved confidently with what we, with the techniques that we use today. So the idea is also that embracing these new technologies might basically allow to simplify the trees that we have today, and also require less custom nodes or custom features that today we have in place to try and achieve some high quality animation. Which all in all very likely reflects on needing less custom tools to maintain, debug, and display what those nodes will be doing. I mean, all in all, this is basically to say that we believe that motion matching makes it viable to develop and maintain your custom animation technology, your custom stack, even for a studio that is not too big. So we started working with this new tech this year, basically starting from scratch. So this is kind of a longer journey. What we're going to share here today is basically it's our initial findings and how we've been doing the normal part up to this point, pretty much. But our long-term goal is really to embrace procedural approaches and trade, animators control for throughput and potentially, the ability of automating animation more. So there's a lot of R&D that we're still planning to do, and our goal is really to have, this system eventually evolves into something that is production ready later next year, and potentially powering, our future titles shipping in more or less in that time frame, which is what we were hoping. Okay, so starting from scratch really meant that we went out there, reading books on the subject, watching GDC talks, video, scavenging the internet for material on animation. And all in all, it feels like there's a lot of good material covering the basic theory, of course, and there's also pretty good and clear explanation covering these new advanced techniques. But surprisingly, it felt like the middle ground, really just putting your basic animation system in place, isn't really that covered. So I thought it could be useful to share what we have been learning in that layer, basically so far. It might give you food for thought if you have a similar system by comparing solution, or might be kickstarting you if you want to start a similar journey. So I'll take for granted basic concepts from animation, of course, but just want to begin with some very quick tips on animation math. So animation math can actually be a little bit counterintuitive sometimes. This is a common example, right? This is showing that basically interpolating direction doesn't really work, like interpolating positions, even though we both represent them as vectors. Okay, so I mean, if you have a background in rendering, then you pretty much cover it. Otherwise, just make sure that you double check some book about basic geometry, pretty much. And on that note, when it comes to animation, using animation math in your code, if you don't have a math library that you trust already, there's several available out there. I can recommend the DirectX Math on PC. Will get you, quite a long way. And even if you have a math library that you're trusting, maybe it's the right time, to use something else for writing your unit test, right? So that you really have a source of ground truth to check against. I mean, these are kind of basic, but yeah, try to not spread your math comment everywhere. Keep it self-contained in a properly named function. And what we learned is that really, comment everything, even everything that looks totally obvious for you now. 2 months from now, you've been changing your code to be vector intrinsic. It might just look like dark magic. So try to be a little bit overboard with that. Okay, so let's actually, let's get started into the core of the talk. So the duty of an animation system at the end of the day is basically to produce a seamless, endless stream of poses, right? Poses for our skeleton. It needs to be seamless. Ideally, we don't want pops or harsh transition. And once again, ideally, we want it to be as physically plausible as possible, right? Stuff like conserving momentum or not having abrupt changes in acceleration and so forth. We're making games, but still we're constantly striving for realism. Of course, unless you're making, I don't know, a remake of Dragon's Lair or some game like that, it's very hard for you to pre-compute everything up front. So reality is that your system needs to constantly create this fake stream by stitching smaller pieces together, right? By stitching clips of animation or even individual frames, individual poses together. So let's start with, you have your set of animations beautifully represented with the blue boxes up there. And your goal is to produce this, endless stream of poses. So question is, okay, how do we combine them? How to go about? So a common approach, as I mentioned before, is really what is commonly called a blend tree, which is basically, it's a tree-based structure that defines how you want to combine your individual animation, how you want to basically layer them. Each node in that graph is really kind of a mathematical operation that is, doing something with its input and passing them over to the next step. Now, some of these animations might have different lengths, some of them might be looping, and overall, in general, you're really dealing with a concept of passing time. So your tree really needs to be, it's not just defining how to blend things, but it also needs to be extended to really account for the concept of time. I like to call this basically stateful animation graphs because, as I will detail in a bit, we need to extend this by storing additional state, generally time management or where we are, to really make this system basically be able to work over time. I'll go into more details again in a little bit, but just assume that each one of those nodes kind of have a concept of a local time. Okay, it knows where it is. And just for reference, this is actually the blend tree for an NPC in Hitman 2. At this level, it's very high level. So this is kind of defining the layering, stuff like head, look at, upper body, lower body, and so forth. And then recursively, each one of those boxes represents another subtree that does more combining of individual animations to achieve what the what's the final desired output really is. Now, surprisingly, you can basically get a lot of ground covered by just implementing these two simple nodes, right? So animation source node, as the name kind of implies, is the node in our new system responsible for sampling the asset data, okay, given the current height, given in its current state. It provides two modes of operation. You can either, just be quick, just fetch the keyframe that is closer to your current sampling time, or generally interpolate between, the two closest frames. Especially if you're making a game where you are expecting to, slow down time, then this is definitely the second way is definitely the way you want to go. Otherwise, your animation will look jerky once you start slowing down your the sampling time. And source nodes in our system actually kind of represent an indirect source, because instead of referencing directly a specific asset as one like that, they really contain just an identifier to kind of point into another data structure that we call the animation database to point to what you really want to use. This lookup is basically only done once, so from a performance point of view, it doesn't really, cause any trouble, but it comes with an additional number of benefits. So the animation database is pretty much a glorified key value store, pretty much. So the keys are high-level names for animation, stuff like jump forward, crouch, stand idle, things like that. And the values in this mapping are the actual resource ID for the actual files that you're going to be, loading memory and using. We use the animation database also. There are certain aspects related to the asset management itself. We basically assume that everything that is in the same database needs to be in memory at the same time, because it will probably, very likely, be used together. And we support arbitrary granularity. So multiple databases can actually be combined and then set on an animation graph to control the look and feel of the animations that are actually used. And the overall goal of this decoupling is really to make sure that your graph, which describes how you want animation to be combined, is not strongly tied to the animations that you will end up actually combining. The usual case is that male and female, they have exactly the same walk cycle, meaning the way the graph is represented, but maybe you want to use different animation for that stuff. So by having this decoupling, you can very quickly support an additional character traits or different gender, just by recording a custom animation for that for the character traits and changing an animation database at runtime. The assets that we load, they're pretty much array of structs. It's a list of what we call tracks. The lion's share, of course, is the bone tracks. So it's an array of per bone we store roto transformation information. Some of the bones we treat them specially. We call them displacement tracks. The idea there is that instead of just being sampled at the beginning to just extract the current frame you're looking at, you will really be you will be more interested in their deltas. We use this to store the trajectories, right? Like your ground bone and things that will basically move also in the world and not just constrained to the animation itself. Other tracks that we're supporting are vector tracks, which generally, you can store floats or vectors in it. We use those for curves and events that I'll cover in more details. One interesting thing we do there, and I'll give more details about this class later on, but we store an hash of what we call a bone list, which is basically a way to quickly catch if your asset's data is compatible with the skeleton that you're expecting to use it on. And from a memory point of view, all the tracks, they're basically stored as interleaved. So when you're sampling a single frame, it's really, it's co-located in memory. So it has a memory-friendly access pattern. Okay, so now we can sample animation. Let's look at the easiest way to actually combine animation, which is a blend two, right? It's the two-way blending between two sources. This by default performs a convex combination between two inputs, and we have a separate mode to basically make it work for additive animation. In that case, the second input will just be added on top, and it's expected to really be a delta. One note there is that a two-way blend node can very easily generalized into handling multiple inputs. And this allows you to kind of flatten trees that you would have been building using just a two-way blends into something that is more flat and easier to manage. On modern processors like PC and consoles, computation is really bounded by memory access pretty much. So doing a little bit of additional branching in the node itself, or at least at the beginning of your outside of your main computational loop, didn't really affect performance for us that much. So what we decided to go was for one node that is just one type of node and it's highly configurable, instead of implementing multiple specialized variation of this. And this N-blend node is really general. It's very can be applied to many problems. For instance, it can easily be used as selector. So let's say you have an array of animations, and just by putting one on the weight that you really care about, it's a quick way of selecting an input animation instead of having to explicitly create yet another custom node just for that. We use it extensively. Now, when you're editing a blend tree, you're pretty much defining how this animation and layers need to be combined. All these inputs, the configuration of some of those nodes, the layout itself, all those things are pretty much immutable. They don't really change at runtime. When you're running your animation graph, then additionally you need to keep track of a little bit of additional state, right? The current time, as I mentioned before. If I don't know how many times you're currently in a loop, are you halfway through a transition, and so forth. So what we do is that we represent in memory each node in the original graph with two separate objects, which we call the configuration part and the runtime part. The mutable part is basically containing the configuration, and the mutable part contains the state while the system is being updated. From a memory point of view, once again, all the configuration node, they're immutable. They're loaded in memory as a single continuous allocation when the resource is installed. They have pretty good locality because, once again, they were already packed to be close to each other. And so they generally result in a once again, cache-friendly access pattern. And a similar approach is actually also used for the runtime nodes, for the state. Once again, they're all in memory in a single contiguous pool. We dynamically allocate them. I'll give more details, but once again, they basically all in the same location. And there's actually a good benefit of keeping them this way and keeping all the state that really matters all together and in a small array. Basically, we can very easily support snapshots, right? We can take a snapshot of the current state by just doing a mem copy. And exactly in the same way, we can restore the state, any arbitrary state of the animation graph just with another mem copy. So the implication is that this can be very easily used for replication. Let's say that you're on a multiplayer game and you want to resynchronize the state of your two animations. That buffer can just be sent over. It can also be used for predictive execution. Let's say that I want to know where my animation character will be in 2 seconds. I can take a snapshot, just execute the graph, read the results, and then roll it back, pretty much. And then it allows very easily to tie into the external debuggers and that kind of things. Now, when you're working with blend trees, a very common and an easy way to manage complexity is to additionally define state machines, right? And what you do is that you basically group in subparts of your tree that are mutually exclusive in substates in a state machine. So, for instance, the animations that are used when in idle, they will certainly never be used when you're moving. This is a really lightweight abstraction, and it can basically be implemented. It doesn't really need a custom implementation. It potentially could just be implemented by the gameplay layers, and everything else could just be a blend weight that switches the blend tree on one side or the other. And we kind of decided to go for that approach, meaning We still expose this through the editing as a feature of the graph, but under the hood, it's really just implemented using something very similar to a blend-N. So pretty much what we do, it's a node where each subtree is one of the inputs. So each substate is basically represented as a subtree. This is an input to the group. And then to support transition, we just control the blend weight for that node to go to 1, and everything else will just automatically go to 0, thanks to the convexity property of the linear combination. Now, transitions. I didn't mention before, but basically, when you have these states, you also define transition, which is your way of going from one state to the other. They will be triggered by the upper layer code and so forth. One of the problems we encountered in the past with our previous tech was that transitions were really inflexible, and once you were in a transition, it could be arbitrarily long, and sometimes the AI had, in the meantime, maybe they had changed their mind, they just wanted to go immediately back to another state. So we really wanted to support transition from transitions, okay? Which is something that gives you a lot of flexibility, but also opens up for a lot of corner cases. Let's make an example. So you have just two states, A and B, and you have one transition to go one way, one transition to go backward. What is really the correct solution if you want to transition back into A while you were already transitioned from A to B, okay? So what's the right thing to do? Just rolling back the transition, kind of canceling it out, but going to exactly the same setup that we had before, or going to a new A, okay? So we decided to just support that second use case. So a transition from a transition, in our case, will always lead you back to a new version of your target state. And this pattern is really employed everywhere, meaning we do dynamic allocation of runtime nodes every time they are activated. So this might sound crazy, slow, from a memory point of view, but I mean, keep this in mind. The runtime part of a node is actually extremely small. As I said before, we allocate all that stuff from a single contiguous piece of memory, which is handled as a circular buffer. So allocations there are extremely fast, because at the end of the day, you're really just moving a pointer. You can use indexes and just manipulate all this stuff basically just with atomic operation on a single location. And once again, since you are creating them at runtime, generally they are spawned close to each other. So nodes that need to be executed close to each other will be close to each other in memory, right? Once again, it's exploiting cache locality. Now, controlling an animation graphs from the upper layer is done through control parameters, right? It's your way of setting a blend weight or setting a target for your IK and so forth. One thing kind of peculiar that we decided to do was not having a separate API for requesting transition, but passing transition requests just as normal control parameters. So a transition request is literally just a Boolean that you will set to true, and then you can configure how you want it cleared. And then we have a small layer on top. It's a helper which allows you, to change control parameters based on a predefined set of curves and how long you want them to take. So events, okay, so you have your animation data, character moving, and you want to mark specific frames having an additional meaning, right? Left footstep, right footstep, begin attaching, some gameplay object that needs to be spawned, and so forth. So we support both, we handle both events that are coming from the data, but also the system itself is raising events while it's being executed. So for instance, transitions, every time a transition is taken or is completed, that kind of generates an internal event that is still bubbled, and it's still our way of communicating to the upper layers that things are happening inside the system. For us, an event is an arbitrary struct, so it can contain anything. What we do is just prefix it with a type ID. So any code that sees an event can, if I know the event, if I can handle it, I will do something. Otherwise, I can bubble it up and just treat it basically as an opaque blob. Yeah, something else that we do is that when events are being sampled, we basically we compute their contribution weight, right? So if two animations are being blended with 50%, 50%, the event that is being raised from one of them will have a weight of 0.5, and so forth, bubbling up, right? So at the end of the tree, you will know really how much that event was really contributing. Now, when it comes to updating, so really doing a step of advancing the state of your network, we treat the update kind of like integrating a function in the in mathematical sense of the term, and practically it's like each node being recursively asked to update its own internal state and doing the same on its active inputs. So the delta time, the dt, that is being requested from the top layer can actually be transformed during this phase, because as I said before, different animations might have different length, or they might have a different starting time. So overall, that dt will be can be scaled up or scaled down or transformed during the update. So during the update, state machines will pretty much check if they need to take a transition or not. Blend nodes will mostly do a big loop on their inputs, and source nodes will sample events and find the keyframes that need to be sent to the upper layers. When it comes to intermediate buffers that are used during this update phase, once again, what we do is that we have a single memory arena that we use it as a circular buffer, and so temporary buffers are dynamically allocated there. Once again, it's pretty fast to do this if you do it atomically. Now, if you're blending animations that have different lengths, but conceptually have phases overlapping, right? Imagine a walk cycle and a running cycle, right? You really want your left leg and right leg to kind of be synchronized. So in this picture, just imagine that the pink slots is the part of those two animations where the left foot is on ground. Okay. So what we do there is that a node can actually access markers, events in its input, and use that to control the DT and achieve a kind of a synchronized blend. To give you an idea, it's basically like we will scale the delta time that is being passed downwards based on the ratio between those sections and based on the current blend weight. So what will happen in practice is that at the beginning, let's say that the top animation has a weight of 1, so it's the major contributor, and the target animation will be kind of squeezed and treated as if it was faster. And as the blending, the crossfading moves from the top one to the bottom one, then we will readjust the time so that at the end, the time for the target animation is its original time, and the time for the source animation will once again will be this time diluted. Sorry. And you can do more you can do more complex stuff, but that should give you the key idea. So for instance, we also have a time scaling node, which is pretty much a pass-through, which just does a multiplier on the DT that it's being passed downwards. Now, so far we've been assuming that all source animation assets, they have exactly the same skeleton. And this is easy and reasonable for a game, but what we really wanted to achieve was being able to compose both our NPCs and our characters by stitching together multiple skeletons and multiple parts, even at runtime. So we needed to have that same level of flexibility also for the animation. So what we do is that we introduce 2 additional objects, let's say that we call bone lists and bone mappings. So a bone list is literally just a list of bones with their names. So you can have 2 lists that share some of the same bones, but maybe have a different length, because one is for your hero, has more bones in the face, the other one maybe is for the NPC, and there are there are less bones there. And then we use a bones mapping, which is basically an integer mapping, to be able to map between the 2. And overall, these 2 things are used to either inflate or filter subsets of your animations at runtime. So we can freely hook source data that has very different length, different sizes, and it's actually coming from different skeletons. And as I mentioned at the beginning, we use the hash bones list to check that there's actually compatibility between what you're trying to merge. Okay. Bones range is something a little bit of experimental. I mean, all of this for us is experimental up to this point, but this is even more. So bones list and bones mapping, they're quite effective if you use them sparingly, but it also means that you could be doing a lot of redundant copies. Okay, so something that we experimented with was the idea of passing along the bones also a range, or actually a list of ranges that you want to operate on. So the idea is, in that case, is that basically all buffers will be actually all at the max size, and only certain sections of it will be used. So we have a modified version of the blend node that basically, instead of doing just a single loop, does a nested loops, right, on each one of these subsections. I mean, we haven't really made up our mind. We're basically waiting for a more solid use case to decide which way to go, because they had some complexity, they reduced some complexity. There's pros and cons, so we haven't really decided. Still up in the air for us. Another concept that we implemented is what we call bone weight masks, which is basically just a list of floats. Pretty much, and once again, we use an hash of the bone list to make sure that it applies to what you believe it applies. And I mean, it's like, if you want to extract the arm-related animation from a full body animation, you will just use 1 on bones related to the arm and 0 everywhere else. Pretty standard. Another node that we have in the system, which helps us achieving a lot of content flexibility, is what we call dynamic hook. And it basically allows dynamically attaching and detaching another animation graphs as a subtree as part of your main tree. And the main use case here is basically animation streaming. So part of your tree can just be used only when, loaded in memory, only when they're needed. And also to bind animation capabilities to game objects instead of the main character. I mean, an example, imagine that you have a special weapon, so all the animation related to that special weapon can live with that weapon instead of being in memory and attached to your main character all the time. Okay. To bone IK, this is something super simple that will still get you, a long way, and it's a very simple analytical solution where you have a 2-bone IK, just fix a focus point for your elbow or your knee, and you will be done, and you will be able to do a lot of things. Now, evaluation of the graph and sampling the animation. So conceptually, that integration phase, when you're updating your network, it's basically done by recursively descending your brand tree, right, from the root to all the active subtree. But I mean, that's really something you don't want to do on a single thread, right? Luckily, this is a tree, so by its own nature, it doesn't have cycles, which basically means it maps very naturally one-on-one with tasks and dependencies. So if you think that that's an example tree, we can just literally convert each one of those nodes in a task that needs to be executed on a worker threads, and the small lines will basically define the dependencies. So we want to run T0 only after T1 and T2 have been executed, but we don't care at all in which order, say, T3, T4, or T5 happens, right? They can be scheduled as pleased, pretty much. So what we do in the animation system is that we literally expose through an API a way for the rest of the engine to hook its own scheduler into it, and then we rely on the scheduler provided by the engine, pretty much. We assume that the scheduling library, scheduling subsystem, provides awaiting capabilities. If you're familiar with C#, just literally think of await in C#, or coroutines. In other languages, basically the ability for your code to yield arbitrarily at any point and be resumed later on without having to manually implement a state machine, resuming state, and all that kind of complexity. And so the beauty of basically doing this and just hooking into a task scheduling system is that now you don't have to deal with fixed phases anymore, right? Some old animation systems, they really have this pre-physics, post-physics kind of concept. You're supposed to, update them twice. But doing this, dependency on any external subsystem, not just physics, but potentially anything, even, an IK full body solver, is just naturally represented as yet another dependency. So it will just naturally be respected as long as your scheduling library supports that stuff. And the added value is that even if you have bubbles in your animation update, because sometimes you have big sync points, everything that is waiting for physics at the end of the day is going to be waiting for a big physics update from the outside. But since you're running on the same scheduler that is running every other workload for your engine, it will be filled with audio or anything pending on to be executed. A few final words about the API that we exposed to the upper layer. So something that we really wanted to enforce was not providing an introspection API. Basically, it's not possible for gameplay code to query nodes by name or read the state of a node. We just didn't want to do that. We want the gameplay code to treat the animation system, an animation graph that is being executed as a black box. Sending inputs down via control parameter and getting outputs through events or the results of an integration. And this is it's coming from our experience with Hitman. So sometimes taking these shortcuts, manipulating nodes directly, it's a very quick way of getting something that you're trying to achieve done. But you will regret it later on, because then you're not allowed to change your graph anymore. Otherwise, you will break gameplay code, which will break something else in turn, and so forth. So there's a bit more than what I covered, but actually not much. So the bulk of this, I think it's good enough basically to get some basic animation systems in place, and that represents a solid foundation on which you can then later on hook more complicated things like, again, motion matching, parametric blending, and so forth. So this is literally where we are at the moment. We started experimenting with these things, with these new things, and hooking them into this basic system that I've described so far. And again, our hopes are that we expect to be able to massively rely on motion matching and similar approaches once we get to production, pretty much. This is the last part. I think we have 5 minutes left. This is like a plot in video games, so we can cut it at any point if needed. So I'll just loosely go through it. Okay, you know how to play animation, how to get your animation into your engine. If you're using Autodesk tools, then FBX generally is a pretty common safe bet. Works nicely as an interoperability format. You can move it. You can move your animation back and forth between most common programs. There's a kind of new kid in town that has been emerging recently. It's called GL transfer format, I believe. We looked into it, but I think it's still not mature. And when it comes to animation and rendering, I've seen so many standards failing to really become standards that I'm not exactly holding my breath for any one of this to succeed. And your third option is, of course, rolling your own. But we've been there before, and I can recommend not to be honest. This is what we kind of decided to set on for us. So Maya and Motion Builder using FBX as an exchange format, and then having our pipeline read the FBX and generate the the runtime format that we really want to load in memory. When it comes to dealing with the FBX, small recommendation: go with the official SDK, even though there's an ASCII version of FBX. But it's don't try to parse it. You're gonna set up yourself for failure pretty much. So the the SDK can be painful to use. I think it's very poorly documented. But at the end of the day, you will spend on this few days a week, and then you're not really gonna touch it anymore. And these are basically the 4 objects that you need to know about and to be able to extract from your data. If you have a pipeline that doesn't like files for whatever reason, say you're on a cloud, well, they support memory streams, even though the documentation says that they don't. Animation events, as I mentioned before, so these are markers and additional data that you are injecting into your raw animation or skeletal bones animation. I mean, they can be used for multiple things, right? As I said, footsteps or marking the section of your animation where you expect to apply more procedural stuff. And here, my only recommendation, the one that it's worth sharing, is that even though you can use, and we used in the past, animation events to drive gameplay code, like, hey, once this event is received from the gameplay code, then do something. I strongly recommend not to. Because you find yourself in a situation where an animator, for whatever reason, deletes an animation tracks, and now suddenly your game is broken, or the NPCs are not opening doors anymore, or they're getting stuff, and stuff like that. And even if you want to go on a server, move your game on a server, and you don't even have a rendering there, right? So you don't even need to really update your animation. Now suddenly your gameplay will depend on the animation being ticked and being fully updated. So my suggestion is use gameplay triggering events just to make the visual better, but if they're not there, always have a timeout, handle them yourself. Pretty much final one, there are multiple options to store your events. You can, and we experimented with storing them inside the FBX itself, or they can be put in a side file. There are plus and minuses. Once again, it's very easy if they are in a separate file. It's kind of easy that they go out of sync. Maybe additional tooling there could help, but keeping them in a side asset also makes it extremely easy to do custom tooling for these things. I mean, in our case, a lot of those events are really used by audio people. They don't really want to use Max or Maya to play around with those things. This one, I'll blaze through it. So especially if you're going motion matching, you really want to use your pipeline to analyze the data, right? Extract, I don't know, linear acceleration, linear velocity, extract forward-facing direction, all those kind of information for each one of your clips and for each one of your frames, because that metadata will be used by the system at runtime to actually run an heuristic, to select what to play next. And it's very important at this phase to really be able to cluster your data sets, to basically analyze how much coverage you have. So am I covering all my turn left, turn right? Is my space of possibility for my character really fully covered? And that also gives you a way of basically knowing where you have too much redundancy, where you don't have enough coverage, and so forth. And that's it.
If anyone has a question, please raise your hand. I'll come around.
Hi, thank you very much for the session. Very interesting. My question is about this multi-threading and computation of animation states and making it use job systems that you have in engine and its relationship with physics subsystem. Do I understand correct that it would be friendly only when we have somehow in-home physics solution, or you could even make it communicate with third-party solutions such as Havoc and physics?
No, you can make it work even with a third party. I mean, most modern physics systems, they also expect you to provide a scheduler from the outside. So as long as you basically hook all of them all in the same systems and you have a way of communicating these dependencies, they will play nicely together.
Yeah, and just follow-on question about also job system and now tendencies to move to data-oriented design. Did you try to combine? Well, I don't know which kind of approach do you use, component-based design or ECS, but if you tried data-oriented design with animation systems.
So that slide where I described the fact that we're basically splitting nodes into, you could claim that that's pretty much data-oriented design, right? We're literally splitting stuff that is kind of cold with stuff that is hot and moving. And for the nodes generally, they're kind of scattered, so it's not super easy to just put them linearly in an array and update all of them. Even though, as I mentioned, in memory they kind of will be there. So still, the access pattern is not exactly linear scan, but it's still somewhat friendly. in our case, the bulk of your compute, once you start profiling this stuff, the vast majority of your time is spent basically doing the major loops, right? I have 2 animations that needs to be blended together, big loop of those, right? Or I have 2 inputs that have been bubbled up, big loop on those. So I don't have exact number with me, unfortunately, but in general, the time to update the tree is really relevant. The vast majority of because basically what you do is that you go through that stuff and it's kind of like quickly scanning through it, spawning tasks, and then those tasks will be the bulk of the work, and they will do it with a linear loop, pretty much.
Okay, thank you.
Welcome.
Hi, thank you for your talk.
Thank you.
My question is more about a gameplay with this system and new Hitman. So the most frustrating situations in previous versions of the game was like when you triggered some situation and excellent phone call, you went away and you came and the game says that the target has left. So you said that no triggers for animation with the gameplay. Is the system helped and the new Hitman?
No, I mean this is fairly low in the in the stack. There are multiple layers, getting your characters to really move. This is a way of playing animations, but that you really need a lot more to make them. So unfortunately, no, it won't. I mean, I'll promise that once I got back, I'll mention this and we'll try to to fix it, whatever it was. But no, this will not really help there.